In this segment, I want to talk about change of phase, about phases of matter. And then I also want to talk about heat flow and what heat does when you add heat to an object. What's the result? That's what we're talking about here. So you probably learned this in other classes, so I'm going to go through it pretty quick here. Three main phases of matter. All elements can exist in all three phases of these phases. Gas, liquid, and solid. In a gas, the particles are only really running into each other and having these quick collisions, right? They're not next to each other. There's actual space between the atoms. And so in this ideal gas model that we've been developing, the only interactions that the particles have between each other is just collisions. So they bounce off each other and that's it, right? And in a gas, again, there's space between the particles. And so, we say that a gas has no definite shape and it has no definite volume. It just expands to fill whatever container I put it in. Here we see this gas is in a balloon, but if I popped that balloon, then those gas molecules would spread out throughout the entire room. Right? So a gas has no specific volume, it has no specific shape. And again, it's because of all that space in between the molecules. Now in a liquid, the molecules are right next to each other, right? So in a liquid, the molecules or the atoms or whatever it is that are the basic piece of this substance, those are right next to each other, but they're not strongly bound to their neighbors. So, right now these guys are next to each other, but then this one might move over here, and then it's got a new neighbor, and then it moves over here, and then it's got a new neighbor over there. So even though the atoms are touching each other, they're not in fixed positions. And so we say that a liquid has a definite volume, but not a definite shape, right? So I could take, 1 cup of water, and I put it in this glass, it's got a certain shape. Still 1 cup, I put it in a different glass, it's got a different shape. Okay, so a liquid has a definite volume, but not a definite shape. Now in a solid, the atoms, the molecules, whatever making up the substance are bound tightly to their neighbors. And so they might be wiggling around a little bit because, of course, unless they're at absolute zero, they are wiggling, right? So they're wiggling around a little bit, but they're bound to their neighbors. And we can think of them as hooked to their neighbors with little springs. It's really quite a good visualization. And so we can store some energy in those springs. They can have some kinetic energy because they're moving. Remember that temperature is a measure of the translational kinetic energy of the molecules that make up the substance. There could be some rotational energy there too, which would contribute to the thermal energy of the substance, but not the temperature, right? So temperature is closely related to thermal energy, closely related to heat, but not the same. Okay, so those are our three main phases of matter. Like I said, all elements can exist in all three of those phases. Now, are those the only phases of matter? No, there's a lot of phases of matter. In fact, I don't know, you might have learned in some class there's 5 phases of matter. I don't know, it's so arbitrary. How many phases of matter are there? I don't know. There's a lot of different phases of matter. Very common ones that we do talk about quite a lot are plasmas. Plasmas are very high energy phase of matter. In a plasma, the electrons are actually removed from the nuclei. And so we think of a plasma as a sea of nuclei of atoms and electrons, right? And the electrons are constantly trying to recombine with the nuclei and then getting ejected because it's such a high temperature, such a high energy phase of matter. And plasmas actually are everywhere. Fire is a plasma. The sun is a plasma. If you look in a fluorescent light inside of a fluorescent light, that is a plasma. Lightning is a plasma. So they really are everywhere around us. In recent years, a new frontier of science has been sort of broken into, and that's the extremely, extremely cold. And it turns out that when you get down to like microkelvin above absolute zero, all kinds of bizarre, strange things happen. There's Bose-Einstein condensates, which is a phase of matter. And actually, the very first Bose-Einstein condensate was created in Boulder right around the year 2000. And they won the Nobel Prize for that, actually. And a Bose-Einstein condensate is just this bizarre phase of matter that exists only in extremely cold temperatures. Like I said, microkelvin, right? Microkelvin above absolute zero. And, very strange things. In superfluid helium, that's another weird cold phase of matter. Superfluid helium, it flows with literally zero viscosity, right? Viscosity is the thickness of a fluid, right? Honey has a high viscosity. Water has a low viscosity, for example. So superfluid helium is this phase of matter that exists at extremely cold temperatures, where helium can have literally zero viscosity, like literally no resistance to flow. And so it'll spontaneously form vortices. It'll spontaneously flow out of a container you try and keep it in. All kinds of very, very bizarre stuff. So there are other phases of matter. In this class, we're going to focus on those three. Okay, so we've said that heat is how we move energy into or out of a system. If it's just thermal energy, right? So, I could add some, here's my system, a fork. I could add some heat to it. What's going to happen to it? I don't know. Here, I got my lighter. I'm adding some heat to my fork. I want you to make a prediction of what's going to happen. You probably don't need physics class to predict that my fork is going to get hot. It's going to increase in temperature, right, to use some precise language. Is it? Ooh, I can't feel it there. Ooh, yeah, there. I don't want to burn my fingers. Ooh, that's pretty darn hot. Yep. You were right. If you put it on a flame, it gets hot. Nice job. You learned some physics. Okay, but wait a minute. It increased its temperature. So adding heat to something increases its temperature, right? Not always. Okay, so now we've journeyed upstairs, and I've got this pot of water here, and I'm going to use my stove to add some heat to this pot of water. Let's see what happens. Okay, I've turned my stove on. And let's see, it's a little bit hard to read there, but the temperature, it's about, it's between 20 and 30 degrees Celsius, and we're adding heat, and hopefully you can see that dial is turning. Indeed, we are adding heat, and the temperature is increasing. This is my most exciting demo I do. It's called Watch This Pot of Water Boil. Checking in, we see that the temperature continues to increase. I am adding heat. The temperature is increasing. Okay, continuing to add heat. Temperature continuing to increase. You probably can't really see that dial that well. Let's see, maybe we can get in here a little bit closer without burning myself. Yeah, it's right about just passing 90 degrees centigrade right now. Getting a little steam on there. Okay. Oh, and now we got legit boiling. Oh man, I'm adding a lot of energy to this pot. Hold on, I gotta turn it down. Okay, so there we go. I got my pot turned down a little bit. You can see it is boiling, and we're getting some nice steam on there. So I am continuing to add energy to this pot of water. You'll notice that the temperature is not changing. So I'm adding heat. But the temperature is not changing. That's different than what we just observed, right? That's different from what we just observed. And I'm just letting this just go, and I'm seeing, boy, it's just stuck right there at about 94 Celsius. Why not 100? Well, because I'm in Fort Collins at 5,000 feet elevation, and water, it only boils at 100 Celsius if you're at sea level. So I'm here at 5,000 feet above sea level. Because of the decreased air pressure, my water boils at a lower temperature. So you saw how quickly the temperature was increasing before when I added heat, and it wasn't boiling. Now it's boiling, and it's been boiling for, a couple minutes now, and the temperature is still just stuck at 94 degrees Celsius. It's just stuck. I'm adding heat, and the temperature isn't changing. Well, where's that energy going? It's going into a phase change. So here I'm changing water from its liquid state into its gas state. And that's where the energy is going, right? Those water molecules in the liquid state of water, the molecules are right next to each other, right? And it turns out they're actually held together with some bonds. Those bonds have some energy associated with them. And it takes energy to break those bonds. And so what we're seeing now is the heat energy that I'm adding to the pot is not going into changing the translational kinetic energy of the molecules. So it's not increasing the temperature of the water. What it's doing, that energy is breaking those bonds between the molecules apart so that they can be separate and it can be in the gas form. So the energy here is not going into increasing its temperature, it's changing the phase. Okay, so now I'm back in my basement, and we've observed that sometimes you add heat to an object and it increases its temperature, and sometimes you add heat to an object and it just changes its phase. So the experiment we just observed involved a pot full of water that I took out of the, I filled up that pot just out of my tap. But let's imagine something slightly different. Let's imagine instead that I took an ice cube out of my freezer. And let's make a little graph here. And on this axis over here, I'm going to graph temperature. Temperature on the vertical axis. And down here, I'm going to graph heat added. And so let's say that I take my ice cube out of my freezer, and my freezer is nice and cold. It's at -10 degrees Celsius. So I just took my ice cube out of my freezer at -10 degrees Celsius. Okay. And I add some heat to it. What's it going to do? It's going to warm up. It's going to increase in temperature. Okay. It's still going to be ice cube. It's going to increase in temperature. Something like that. Until when? How long is that going to happen? Well, it's going to increase in temperature until it reaches the melting point of water. Where's that at? Well, that is at 0 degrees Celsius. Once it reaches the melting point of water, I'm going to add some more heat, but it's not going to change the temperature. It's going to go into breaking the bonds that are making the ice crystals. And so I'm going to add some energy, but it's not going to increase in temperature until all of the ice is melted. So at this point right here, I have ice. And at this point right here, I have liquid water. But they're both at the same temperature. It just took some energy to melt it. Now, once I have liquid water, I can add some energy, and its temperature will increase. Till when? Well, until it reaches the boiling temperature of water. Which, as we just saw here in Fort Collins, it is about 94 degrees. I don't think that thermometer is super accurate. I think with more accurate thermometers, I've measured 91, 92 before. Somewhere in there. But let's go ahead and use our standard value. Imagine we did this experiment at sea level. Then this would be 100 degrees Celsius. So at 100 degrees Celsius, that's what we were observing upstairs. I keep adding energy, but the temperature doesn't go up. It just changes the phase. It boils that water away. It stays at a constant temperature until what? Until it's completely evaporated. We didn't get to this point upstairs. And then if I was able to add energy to it, it would continue to increase in temperature. So at this point right here, I still have water. But at this point right here, I have steam or water vapor, right? So we see that sometimes we add energy and the temperature changes. Sometimes we add energy and the phase changes. Okay, so we have equations for these two different situations. Let's look at the PowerPoint. Adding energy, heat energy, will raise temperature, but it could also change the phase. So if I'm in one of these sloped regions, then the equation that governs that is Q equals mc delta T. What are each of these pieces? Well, Q is heat energy, M is mass, C is a constant. It's called the specific heat capacity. And what C tells you is how much energy does it take to change the temperature of a substance by 1 degree? Because it's not the same for every substance. In fact, an object or a substance like water, it takes a lot of energy to change the temperature of water by 1 degree, and it takes not very much to change the temperature of, say, aluminum. For example, if you had 1 kilogram of water, then you would need 4,190 joules in order to increase the temperature of that water by 1 degree Celsius. However, if you had a kilogram of aluminum, you would need only 900 joules to increase the temperature of that piece of aluminum by 1 degree Celsius. And so those two numbers that I just gave you, those are examples of specific heat capacities. And that's the C. C is the specific heat, and it tells you how much energy it takes to change 1 kilogram of a substance by 1 Kelvin. And so here is a chart. Of course, you don't have to memorize these things, but you can see that water, right, has this very high heat capacity, 4190. It's amongst the highest of sort of everyday substances. Notice how much higher it is than some of these other metals, right? In fact, it's something like a factor of 40 times greater than lead. That's interesting, right? That means it takes 40 times more energy to change 1 kilogram of water by 1 degree than it does to change 1 kilogram of lead by 1 degree. Sort of surprising, actually. And the fact that water has this really high specific heat, that's why, water makes a great place for storing thermal energy. In the olden days, if you read some book about prairie life, they used to take a hot water bottle to bed at night. Right? Why? Because it contains so much energy. It can keep you warm all night long. Much better than a hot piece of gold, although that might make you feel satisfied in different ways. So anyway, very interesting. This high heat capacity of water, it's also why coastal regions have much more moderate temperatures than inland regions. Here in Colorado, as you know, we see huge temperature swings. We can have, 50 degrees or more between night and day. You don't see that on coastal regions. If you live in Seattle, you might have 10 or 20 degrees between daytime and nighttime. Why? Because you're surrounded by water, and water takes a ton of energy to heat up. It releases a ton of energy when it cools down. Okay, so this is our equation, again, for how much energy it takes to change a certain amount of a certain substance by a certain number of degrees. Okay, so that's these sloped regions of this graph. But we also saw that sometimes you add energy and we have a change of phase. Right? And so that's what these equations are for. So sometimes we need to add energy or take energy to melt something. That's where we use this equation here. And this is the latent heat of fusion. And it plays a similar role to the C, the specific heat up here. We call this the heat of transformation. And so if we're talking about fusion, then that is the heat it takes to melt a certain amount of a substance, or alternatively, the amount of energy that is released when a certain amount of a substance freezes, right? So this is all about the energy between a liquid and a solid, and the latent heat of vaporization. This describes the energy involved when things change between a liquid and a gas. Okay, so we've got these equations here, right here. Notice they're plus minus, right? If we're moving this way on the graph, then we'll use plus, right? So everything in this direction, we use plus. In other words, if I'm adding energy, we use plus. If I'm taking energy away, we would use minus. That's what those plus and minus means, right? Again, if I'm adding energy to something, I'm melting it. I'm making it vaporize, right? If I'm taking energy away, then I'm making it condense. I'm freezing it. Okay. Again, this is the latent heat of vaporization. This chart also tells you the boiling temperature and the freezing temperature for various substances. It's likely that if you've had a chemistry class, you've solved calorimetry problems. And so calorimetry problems are this idea where we take some insulated vessel, we add some hot stuff, we add some cold stuff, some stuff melts maybe, some stuff evaporates, I don't know. Some things happen, and I tell you what I put in, and I ask you what's the final temperature. Or I say, I've got a cup of coffee, how many ice cubes do I have to add to it to get it to a certain temperature, right? So those are the kind of questions. It's like I put a bunch of things at different temperatures and maybe different phases in an insulated container, and I ask you some questions about it. That is calorimetry problems. And so a calorimeter is this insulated container. So a calorimeter is some sort of a scientific thermos, let's call it that, where we can make measurements on the inside, but ideally we have no heat flowing in or out. And that'll be the general assumption we'll make. We'll assume we have a perfect thermos as our calorimeter. So if we're approaching a calorimetry problem, then what we do is we want to identify the interacting systems. And again, this makes it hard, makes it sound hard. It's not. You're going to put a bunch of stuff in a container. Your interacting systems is all the stuff you put in there. When we practically get to solving problems, it's not too hard. Now, this is basically conservation of energy. And I really like it. Like I've said before, conservation of energy is one of my favorite topics. And so calorimetry is really just conservation of energy, but applied to thermal energy, right? Applied to only thermal things. And so, you know, if I put some hot stuff and some cold stuff into a thermos together, well, let's think about the energy. Well, the hot stuff is going to lose energy, and the cold stuff is going to gain energy until they reach equilibrium, until they're at the same temperature, and then heat will quit flowing. Remember, our definition of temperature, one of them is, it's the thing that is the same when heat stops flowing between two substances, right? And so we can kind of turn that in reverse and say, well, heat will continue to flow between the two substances until they are at the same temperature. Once they're at the same temperature, we say thermal equilibrium has been reached and heat no longer flows between them. Okay, well, how does the amount of energy that the hot stuff lost compare to the amount of energy that the cold stuff gained? They're exactly the same, right? They're exactly the same. In other words, whatever was lost by the hot stuff is equal to whatever was gained by the cold stuff, which means that the total change in energy of the system is zero. That's where we say, hey, we have a calorimeter, a thermos, that is completely sealed in the sense that no heat can flow into or out of it. And that's what this statement says right here. It says, well, no matter however many things I have, some of them are going to gain energy, some of them are going to lose energy, but as long as we have a perfect calorimeter, the total energy change of the system will be zero. So it really is just a conservation of energy problem. We're going to use MC delta T for any systems that undergo a temperature change. So any of our substances that are increasing or decreasing in temperature, we need to add an MC delta T term for those. And for systems that undergo a phase change, it's M times L. And again, this L, we need to be sure to distinguish whether we're looking for the latent heat of vaporization or of fusion. And again, plus if we're adding heat, minus if we're taking heat out. Okay. So, sometimes you might have things that have a temperature change and a phase change. And then we should be sure we look at our final answer and assess, did we end up with something that doesn't make any sense? It's real easy to have sign errors when we're doing these type of problems. Okay, well, let's try an example. If you placed a 10-gram ice cube at 0 degrees Celsius into a cup of hot coffee containing 500 grams at 90 degrees Celsius, what would be the final temperature of your coffee? And then I give you a bunch of constants. Okay, so first of all, this is a calorimetry problem. And yeah, it's a coffee cup, not a thermos. That's okay. We're going to assume this happens fast enough that a significant amount of heat is not lost or gained. So this is a calorimetry problem. What's gaining energy and what's losing energy? Well, the coffee is losing energy because the coffee is hot and it's going to cool down. The ice cubes are gaining energy because they start out cold and in ice form. They're going to melt and then increase in temperature. So the ice is gaining energy. The hot coffee is losing energy. But since those energies are equal, the total change in energy of the system is zero. So that is where we will want to start our problem-solving process. We'll say Q coffee plus Q ice equals 0. And we're going to take a couple of steps here and kind of do it one step at a time. So, Q coffee. Do we have any phase changes involved here? No, the coffee starts out as liquid, it's hot, it's going to cool down, it's still liquid at the end. So, we just have Q, and I'm going to be real specific with my subscript, since this is the first problem like this we've done. So this is Q to cool the coffee. Okay, so then we're also going to need the energy to melt to the ice, because that's the first thing that has to happen. And then we're going to have to warm the ice once it's melted. Okay, that equals 0. So again, we got 3 terms here because we got to warm up the we got to cool down the coffee. We got a term for melting the ice and a term for warming up the ice. All right, let's plug in our little equations for these. Q, this is a change in temperature. So this is an MC delta T. And so this needs to be mass of the coffee. C coffee, we'll just assume that C coffee is the same as C water. C of the coffee times delta T of the coffee. Now, ice melt. This is going to be an M times L term. Is it MLF or is it MLV? Well, here we are talking about the phase transition between solid and liquid. So this is MLF. What goes here, positive or negative? Well, is the ice absorbing energy or releasing energy? The ice is absorbing energy, so a plus goes right there. And then we have a delta T for the ice. With the MC delta T terms, you don't ever have to worry about positive or negative if you set it up like this, because the delta T will take care of it. There's always final minus initial. So delta TC will be negative, making this whole term negative because the coffee's losing energy. But my point is, we don't need to intentionally put the negative out in here. The delta T takes care of it. However, for the change of phase, we do have to make a conscious decision what goes in front. So for this delta T, or for this MC delta T, we just write plus. This is going to be the mass of the ice, C. Ooh. Should we use the specific heat of ice or the specific heat of water? It was ice when I put it in my coffee. But now that it's starting to warm up, it's already melted, isn't it? So this needs to be the heat capacity of water. And that's delta T coffee equals 0. Okay, doing good, doing good. Oh, which mass here? I need to be sure of my subscripts. That's mass of ice, isn't it? I'm looking for the final temperature of my coffee, aren't I? So I think I better break into this a little bit. We're going to have to do a couple lines of algebra here. So we're going to have mass of the coffee, and again, C of the coffee. We're going to assume that coffee and water are the same there. And so then this would be T final. I don't need to have T final coffee because everything's at the same final temperature. Minus T initial of the coffee plus mass of the ice, LF, plus mass of the ice, C of the water, times, again, final minus initial, T final minus initial. What was the initial temperature of the ice once it's melted? 0. Now some of you are saying, hey, wait a minute. Don't you need to have that temperature in Kelvin? That'd be fine. You totally could convert that to Kelvin. But remember, if we're dealing with a delta T in Celsius is exactly the same as delta T in Kelvin. As long as the only T's that show up in our equations are delta T's, then we can use Celsius and we'll be just fine. Okay, so we're looking for T final. You can see we do have a little bit of algebra ahead of us. First thing I want to do is get rid of my parentheses. Now I should get everything with a T final on one side, everything without a T final goes on the other side. Factor out my TF and divide by the leftovers. Oh heck, I've got a seawater I could factor out too, huh? Now I'll divide by the leftovers and I'll have an equation. Okay. Now I can plug in my numbers. And so I've plugged in all my numbers here. I kind of ran out of room on my board. And so I jumped to the exciting conclusion, 87 degrees Celsius. You know, a few things like we already mentioned, you don't have to convert your temperature into Kelvin. Why? Because the only temperatures that show up here are delta T's. And so we're all set there. Be sure you convert your masses to kilograms, though, right? Because notice that in the latent heat of fusion and the specific heat, those are per kilogram. So you do need to convert those to kilograms. Yeah, I think that's about it. Okay.